Hello everyone, I'm Lian from Peking University. Today, I'm going to talk about automatic linear resource bound analysis for RaRust via prophecy potential. This is a joint work with my advisor, Wang. So, I will first give a simple introduction to RaRust. RaRust is a popular system programming language renowned for its unique capability of memory management. It provides precise and safe memory control without requiring garbage collection. To ensure memory safety, preventing issues like dangling reference, RaRust employs a sophisticated type system that performs static checks at compile time. Compile time, instead of runtime checking, enables programmers to write reliable and efficient code. While zero-cost abstraction like this RaRust targets high runtime performance of programs. The RaRust compiler checks the memory safety of programs. However, memory safety does not naturally guarantee good performance. RaRust programmer may write memory-safe but poorly performing programs. Resource analysts, especially the automatic one, helps RaRust programmers understand the performance of their code. By comparing the results with their expectation, programmer can gain confidence in code efficiency or identify opportunities for optimization. This is why we want to do resource analysis for RaRust programs. To do resource analysis, we will introduce a prior work on resource analysis, the approach called AARA, Automatic Amortized Resource Analysis. The second A is the amortized, which indicates that AARA uses potential method. Suppose we have a program with full and bar and 3 program states. AARA associates each program state with potential information. When AARA system checks the program, it will collect constraints between the resource consumption and the potentials. For example, we define a recursive function over a list of integers in RaRust to calculate the sum of all integers in a list. We plot the control flow graph on the right, where S0 through S4 identify program location highlighted in the program. The tick statement in the const case specify a cost metric that each recursive call consumes 10 units of resource. AARA extends data types with symbolic potential according to their structures. In our example, we have a single numeric symbol P for the list type, which means that every const carries P units of potential. So the potential of a list should equal P times its length. Different states could have different potential, so we use P0 through P4 to denote symbolic potential of L at different states. AARA collects constraints among those symbols. For example, AARA collects 1 when checking the statement between the state S1 and S3, the const case, which tells the potential difference should be at least 10th. With all constraints collected, AARA uses a constraint solver to solve these constraints to assign concrete numbers for those P's. In this case, it assigns 10 to the P0, which means that the resource usage of the sum function is upper bounded by 10 times the length of the input list. So when we apply AARA to RaRust, we will encounter several challenges. One primary issue lies in defining the potential of the mutable reference. We illustrate this with an example. It creates a mutable reference to the list. The program can be described in 2 states, S0 before the reference is created and S1 after. At S0, there is a single variable, L, and it carries some amount of potential. At S1, there are two variables, one L and the another the reference P. Since the operation solely involves creating a reference to L, it seems that the potential of L should remain unchanged. As for the resource of the mutable reference P, a natural intuition suggests that P should carry the same potential as L, since referencing the potential of L can access the original variable L. However, this approach violates an important invariant. The total potential should be conserved. Simply summing up the potentials of each variable at S1 will introduce additional potential. In this example, exactly it doubled the potential. So, to address the challenge outlined above, we leverage the RaRust type system, which enforces that the mutable reference is exclusive. Returning to the example, after creating the reference P and before it is dropped, that is, during the lifetime of P, the original variable L becomes temporarily inaccessible. We cannot assign to L. Otherwise, the RaRust compiler will complain that you cannot do this. The exclusivity leads to a natural intuition. The potential of the list L is transferred to the reference P, as illustrated in the animation. But then another problem is that when the lifetime of P ends, the potential should be returned to L for the RaRust computation. Even the relation here between L and P is simple, but in general, it is not compositional to check the reference relations. Therefore, we propose our key contribution, the notion of prophecy potential. It is termed prophecy because it anticipated a symbolic potential at the beginning of P's lifetime. But it represents the amount of potential that L is expected to get back at the end of the P's lifetime. Under this formulation, the potential of the mutable reference equals the initial potential, the red one, of L minus the prophecy potential. We will realize the prophecy while adding a new constraint at the end of the P's lifetime. The potential associated with P must be non-negative, so it can return sufficient amount of potential to L. With prophecy potential in our approach, the analysis of mutable reference is decomposed into two independent stages. When the mutable reference is created, a prophecy potential introduced. When the reference is dropped, a constraint is generated requiring that the potential of the reference must be non-negative. In this way, we do not need to check the relation between L and P at the end of the lifetime. These two independent stages are integrated via the generated constraint. Prophecy potential therefore enables compositional reasoning about the mutable reference. To evaluate our methods, we set up an experiment. We have implemented a prototype resource analyzer named RaRust, based on RABC compiler and a front-end plugin column. Here we present several cases. We support mutable reference, as mentioned above, and nested reference, and immutable reference. We support recursive function and loops. We also support different user-defined data types, not only lists, but also trees, tuples, and others. All results are expressed as linear bounds, just as our title states. Although this is not a fundamental limitation of our approach, prior AI systems have been shown to support more expressive bound forms such as polynomial, exponential, and others. To summarize, we have introduced a novel approach for resource analysis in RaRust using prophecy potential. The key insight lies in effectively leveraging RaRust's powerful type system to enable fine-grained resource analysis. The main highlight of our approach is the introduction of the prophecy potential for mutable reference. This allows us to soundly check and transfer resource through mutable reference compositionally. In addition to our main contribution presented here, we also have some other significant contribution detailed in the paper. For future work, we do not support in this work for the unsafe code, closure, and nonlinear bounds. So thank you for listening to my talk. I'm happy to answer your question.
Questions? All right. Well, then let me warm up the audience. So it seems like that the prophecy potentials are very much tied to the sort of borrowing system in Rust. So in what ways could this be generalized, or?
Sorry?
So, so to what extent is the prophecy potentials tied to essentially the borrowing mechanism in Rust versus maybe other applications where you can infer some relationship?
Let me think about. So we extend the prophecy potential for the mutable reference, of course, for the borrow and ownership system for the RaRust programming language. So I'm not sure whether my answer exactly answer your question.
All right, we can discuss offline since we have another question.
Hi there. Thanks for the very nice talk. I wondered, so you mentioned some of the Rust types that you support in your approach. I wondered what would it take to extend the approach to support fancier Rust types, for example, structs that store references in their fields, etc. Do you think the approach could be extended to this language of types too?
Okay. The question is about how to extend to support more types for the Rust. We support the box type in this work, and we support the user-defined data types using a uniform template for the enum types for the ADT types. As for the types such as cell, web cells, vectors, and some other types in the standard library, they use unsafe code, inferring, mutable. We do not support in this work, and we are considering to handle this for them, because although they are unsafe code, but they are typed as safe API, so we can give them resource annotations for the safe API, and maybe we can add some testing to generate it, the annotation automatically. We are considering to do this. Thank you.